Now, in this video, I want to discuss the question 8A of the 2010 Catholic Schools Trials for Extension 2. Now, this question 8A is an example of when question 8s are easier than the questions preceding it and should be attempted as much as possible. Now, you might look at this and think, well, that's a lot of algebra there, but in fact, they did most of the writing for you. This question is easy enough in all three of the parts to do. So in the first part it says use mathematical induction to prove that if you have this function and you want to differentiate it n number of times, then you're going to get 2 to the power of n at the front. But I mean, just by observation you can see how every time you differentiate this you're going to get a 2 out the front. So why do we even need induction? Well, they are awarding 3 marks for your mathematical induction structure. So you might as well bite the bullet and do it. At this stage in the exam, you probably are short on time, but if this is something that you can do, put that 5 minutes aside, take a deep breath, and write it out. It's very easy. Power series of a function. Now, don't get off foot by all this stuff over here because you found what each of these things are, right? Each of these are just a substitution of 0 into the value of x. So when you have 2 to the power of n, e to the power of 2x, well, at 0, x equals 0, these are just the corresponding values. So that's just going to be 2 to the power of 1, 2 to the power of 2 is 4, to the power of 3 is 8. And this is just a straight out substitution, and all you had to do was just find the value of f0, f-0, f-0 and write it out. Now, part 3. Given that tan is this, now you might think, hey, don't we deserve to see a little bit more of it? Maybe we want to know how this 15 came about and all that, but the question is so easy if all you did was just write out this limit very carefully using the information you were given, namely this and this. So let's write that out. What it would look like is very simple. You're going to have the limit as x approaches 0 of 1 plus 2x plus 2x squared minus e to the power of 2x all over tan x minus x. Now, quite simply, the first thing you look at is e to the 2x. Now, e to the 2x is really, I'll just write it out neatly here, 1 plus 2x squared minus, in brackets, 1 plus 2x plus 4x squared on 2 factorial plus 8x cubed on 3 factorial, so on. On the bottom, you're going to have tan x, which is x plus x cubed on 3 plus 2x5 on 15 minus x. Now, you can look at what's going to cancel out here straight away. Oh, and so on. I forgot to write the so on part of the tan, right? It goes on forever, minus x. What cancels out is this cancels out with the 1, 2x cancels out with the 2x, 2x squared cancels out with 4x squared on 2. And what you're really going to have on the numerator is just negative 8x cubed on 3 factorial plus a whole bunch of other things. And all these things are going to have higher powers than x cubed. On the bottom, these two cancel out, and you're going to have x cubed on 3 plus 2x5 on 15, and so on. So on the top are all negative terms, on the bottom are all positive terms. Now you might think, okay, well, we're stuck, right? We can't really find the limit of these things. But fortunately, what actually happens is that as the limit approaches 0, the only things of relevance is the x cubed. Because x5, x4, or any other higher powers of x decrease faster than x to the 0. Now, if that doesn't convince you, I'm trying to say that what will actually happen is that these terms are negligible in terms of their value as x approaches 0. So all it's going to come towards is you're going to have minus 8 on 3 factorial over 1 on 3. And that's going to be minus 4 as your answer. Now you might think, oh, that was a bit sort of anticlimactic, you know, is there more to be said for this question, for the 2 marks that is awarded? Well, not really, no, because, you know, you could go roundabout and say, all right, great, why don't we change this x to u and let u be 1 over x and rewrite all of these, but again, you'll realize that as x approaches 0, all of these are going to approach 0, and these things approach 0 faster than x cubed. So these ones vanish faster, and you just stick to focusing on the first term of the numerator and denominator. If you're still feeling uncomfortable about this, you can always use L'Hopital's, okay, and say that because they are both approaching 0 and the top and bottom are going to both approach 0 in terms of their actual value, you know, if we're doing 0 over 0, well, limit, then you can just differentiate this several times and realize that on the top, you're going to have minus 8 on 3 cubed, okay? L'Hopital's rule says that it's going to be minus 8 on 3 cubed, and that's going to be the derivative of x cubed, which is 3x squared, times the derivative of x squared. So we just differentiate the top 3 times, so 3 times 2 times 1. And on the bottom, we're going to have 1 on 3, differentiate it as 3 times 2 times 1 as well. But the other ones, they're still going to be x, you know, bunch of x's, bunch of x squares, and these things disappear because when you go to 0, these things disappear, and in the end, you just have a fraction anyway. Okay, just to clarify what I just did, I said x cubed, differentiated becomes 3x squared, differentiate that becomes 3 times 2 times x, differentiate that becomes 3 times 2 times 1. Now, if you're not sure what L'Hopital's rules is, it basically says that if you're taking the limit of x to the power, towards 0 of a function over another function, if both of these functions approach 0, then you're allowed to differentiate it, and the limit is the same as the limit of the derivatives, okay, as the numerator and denominator. But it turns out that if you just differentiate it once, it's not enough. It's still going to be 0. Differentiate it again until you get something that's not both 0, as you can see in this case. So the ratio is just going to be minus 4.